Hello everyone. Today I want to introduce our paper accepted by CVPR 2023 named Raw Image Reconstruction with Learned Compact Metadata. As an unprocessed image format, raw images have unique advantages compared with sRGB images. For example, they have more room for post-processing and artistic manipulation. Besides, better performances are achieved in downstream tasks like low-light image enhancement due to the linear relationship between the pixel value and the photon count. Although having many advantages than sRGB image, the large storage requirement limits the application of the raw format. For example, the two images have almost the same visual quality, but they have a large difference in terms of file size. To reduce the storage overhead, one way is to convert the sRGB image back to the raw space using a learned network. However, due to the information loss of sRGB image, the fidelity cannot be guaranteed. Most recently, a strategy of raw image reconstruction is proposed to additionally utilize the saved metadata to reconstruct the raw image as shown in this framework. In a paper published in WACV 2021, a uniform sampling of the pixels in the raw image space is proposed. The sampled raw pixels are used to solve a system of linear equations from sRGB to raw image. Most recently, in CVPR 2022, the work further improved the previous sampling strategy. Specifically, instead of a uniform sampling, this work proposes to utilize a superpixel-based strategy to learn a non-uniform sampling. As shown in this figure, the image signal processing pipeline involves a series of non-linear mapping, and the information loss caused by ISP is also non-uniform. Therefore, the saved metadata should be globally non-uniform to achieve higher storage efficiency. Motivated by that observation, we propose to directly optimize the metadata we saved in an end-to-end manner. Specifically, existing works aim to save a sparsely sampled raw pixels as metadata, which has spatial and precision redundancy. Even for the most recently SOTA method that the sampling is locally non-uniform, it is still uniform from the global perspective. Therefore, they lead to suboptimal solutions. Instead, we propose to sample in the latent space. In this way, different bitrate can be adaptively assigned to different areas, and the learned metadata will further be encoded and compressed into bit streams. The overall framework of the proposed method is as follows. We propose a fully end-to-end framework to learn the compact metadata based on an encoder and decoder manner. A hyperprior model is used to further reduce the spatial redundancy in the latent feature. To further improve the coding efficiency, we propose a novel sRGB guided context model. The principle of context models is to use the already processed latent features to better modeling the distribution of the to-be-processed latent features based on the fact that the neighboring latent features usually have similar values. However, previous context model are usually based on an autoregressive model. In the other word, the latent features are encoded or decoded one by one, which greatly increases the inference overhead of both compression and decompression processes. To accelerate the inference speed of the context model and enjoy the merit of the context model at the same time, we propose a novel sRGB guided context model. The details of the proposed sRGB guided context model can be seen in this figure. The core of the proposed context model is the order prediction module, which output the mask of latent features to be processed at each step. Since the mask operation is not differentiable, we propose to use the Gumbel softmax technique to enable the training. Besides, the same predefined random matrix from the Gumbel distribution are used for both compression and decompression to ensure that they have exactly the same ordering mask. Compared with previous context model, the proposed one can finish the whole process in a few steps, which greatly speed up the inference speed. We evaluated the proposed method on two widely used raw image datasets, that is, Adobe 5K and NUS dataset, and compare the proposed method with previous SOTA methods. As shown in the table, the proposed method achieved the best performance with smaller metadata. We also evaluate the performance of the proposed model on JPEG image with different quality factors. The proposed method also stably outperforms existing methods in a large margin. We evaluate the effectiveness of the context model and find that it can greatly decrease the size of metadata compared with the method without the context model. We also achieve comparable or even faster speed than existing works. We further evaluate the performance of the model on shadows and highlights since they are more challenging areas. As shown in the figure, directly enhance the visibility using JPEG image will lead to strong artifact. However, if we additionally utilize a small amount of metadata from the proposed method, we can achieve much better reconstruction quality. Thanks for your listening.